Let's look at this theory, which is really simple theory: maximum normal stress theory for brittle materials. Okay, this theory states that failure occurs when one of the principal stresses equals or exceeds the strength. Okay, so what we do is we do the same thing we've done all over this course, which is we arrange the stresses, the principal stresses, as sigma 1 is the maximum stress, okay, and sigma 3 is the minimum stress. And since sigma 1 is the maximum stress, we have it failing when it reaches the tensile strength, and then sigma 3 failing when it exceeds the compressive strength. So you'll have to choose the bigger of those two for failure. So this is SUT is the ultimate tensile strength. SUC is the ultimate compressive strength. Okay, so that's when failure will occur. However, if you want to use this criterion for design, then what you do is you'll introduce a factor of safety. So the design equations will be sigma one equals SUT divided by N, and sigma 2 equals minus SUC divided by N. Now, if you have a plane stress condition, then sigma 1 is, this should be sigma 3. Sigma 1 is, okay, so let's just assume that sigma 1 is sigma A, and sigma 3 is sigma B. So if you draw this on the plot, we've been drawing for the past for the ductile materials, it just says that you would have something like this, a box or a square. However, this coordinate is SUT minus SUC minus SUC, and then clearly the failure region is anything outside this yellow region. No failure. Because that's a really simple theory, and you'll see that has its own limitations. Okay, so there's one theory for brittle materials. Here we'll talk next about the next two theories in one section. So the next one is, we are in 509, and we'll talk about Coulomb, Mohr, Okay, here there are two theories we'll talk about. One of them is called the brittle Coulomb-Mohr theory, and this is similar to the ductile Coulomb-Mohr theory. It's to be used when the compressive strength, sorry, the failure in tension is different from the failure in compression. So there's a distinct SUC, which is different from SUT. For ductile material, that's usually not true. For brittle materials, it's usually true that there is a different compressive failure than a tensile failure. And then there's the other one is the modified Mohr theory, which overcomes some of the limitations of the brittle Coulomb-Mohr theory. Let's do the brittle Coulomb-Mohr theory. Okay, so this is, as I said, is it's almost identical to ductile, similar to ductile Coulomb-Mohr. Okay, so what's the Coulomb-Mohr theory for ductile material? It says that sigma A, so this is for failure, right? Sigma A equals SUT when the strengths or the principal stresses are greater than 0 or they're positive. It's this particular line given by this equation, SUC equals 1 if one of the stress is tensile, so sigma is tensile, sigma B is compressive. And then if both the stresses are compressive, then you'll just use S sigma B equals minus SUC. That's when 0 is greater than sigma A greater than sigma B. Okay, so we have done a plot for this. I'll just redo it. Plot is identical to the one we did for ductile Coulomb-Mohr theory. So these are our tensile limits. Now, assuming that SUT is less than SUC, SUC is say minus SUC, and the same distance here, minus SUC. Okay, so that's the first quadrant and the third quadrant, they look like this. But in the second and fourth quadrant, we just need to join these lines. So that's our, this region in yellow is the non-region where failure will not occur. Anything outside that will be a failure. Okay, so now let's see how both these theories compare with actual experimental data. So the way the experiments are done is you take a test specimen and you load it in tension first, and then you keep increasing the stress till it fails. You do the same thing with compression, and then again measure when it fails. If you do that, then you get these circles, which are shown here. So these are plotted on the same sigma A, sigma B plot, and this is for certain alloy. I'm blanking on which alloy this is. Okay, so the maximum normal stress theory is plotted here. It's basically going to be that square I showed you, but sigma ut and sigma uc are the coordinates which are used to draw it. And then we can draw the Coulomb-Mohr theory, which is this line, which I just drew some time back, right? So if you notice, there is no data in this region, and there's no data in this region, but there is data in the first quadrant and the fourth quadrant, okay? The data on the, first of all, the Coulomb theory and the maximum normal theory in the first quadrant are pretty much the same, that line. And the data sort of lines up well with those theories. So in the first quadrant, both those theories agree with each other. Also, the data agrees. So we are good in the first quadrant. This is the first, this is the second, this is the third, and this is the fourth. That's the usual naming convention for quadrants. Okay, so the fourth quadrant is where there's a problem. We have the maximum normal stress theory, MNS, and then we have the Coulomb-Mohr theory, which is shown by the dashed line. Right? We see that the points, the experimental points, lie on the maximum normal stress theory for a bit, and then they sort of veer off. Right? Here there are some points which sort of agree with the MNS, sorry, the CM theory. But these points, all these points over here, we show them in the green. So they do not agree with CM or MNS. Okay. So there's a problem, which is those points don't agree. So what people do is they modify the CM or Coulomb-Mohr theory so that the points will agree. So what we can notice is that these points follow this line up to SUT, and then it sort of goes towards this point, SUC. So this new theory, which I'm going to write in a bit, the modified Mohr theory will actually take into account these points as well as the other points. So this is where the modified Mohr theory comes in. So I'll quickly make some notes here. 1, CM agrees with MNS and data. 2 and 3, there's no data. And then 4, MNS agrees with some data, and CM, it does agree here. So you can say CM and MNS agrees with some data, right? The data in blue. So CM agrees where the data is blue, and this one where I marked it in red. Okay. So the green are the where the data does not follow MNS or CM. So this is where the modified Mohr theory will come in. So modified Mohr theory fixes these issues. So I'll talk about, I'll write the equations. The equations are something which help us to put these the dots in the red circle, or red ellipse, the blue ellipse, and the green ellipse together in a single in an equation which now captures the entire set of data points. So let's get to modified Mohr theory, which is going to be the last one. So B is the modified Mohr theory. Yeah, I'm just going to put the equations down because it comes from basically curve fitting. So sigma A is SUT, and that is true for sigma A greater than sigma B is greater than equal to 0. It also is true when sigma A is greater than 0, greater than sigma B, and the ratio of sigma B divided by sigma A with the absolute value is less than 1. Okay, so this is one part of the equation. Then there's another equation, SUC minus SUT divided by SUC SUT, the whole thing multiplied by sigma A minus sigma B divided by SUC equals 1. Okay, this is true when sigma A is greater than 0, greater than sigma B, and the ratio of sigma B divided by sigma A with the absolute sign is greater than 1. And the final equation is sigma B.
The absolute of the sigma B and sigma A, that's completely separate from the other thing, right?
Yes.
Okay.
This. Sigma B is equal to minus SUC, and that's true when both stresses are compressive. If you like, this is 1, this is 2, this is 3. Okay, so what I've put down there is basically the necessary equations to fit those data points to those curves. Yeah, question? Yeah.
Or is that multiplied by sigma A?
Okay, so is that what you're saying? Yeah, it's one thing. Okay, so how does this failure region look like? Okay, so first of all, the first quadrant remains as it is. So SUT, SUT. The change happens in quadrant 2 and 4. So what will happen is we need to draw the line for SUT. So this is also SUT, SUT with a negative sign. And so then this line basically extends till SUT. After this, it sort of goes towards negative SUC. Just draw that. Okay, so it will go towards SUC. See, and in the third quadrant, it pretty much is a box or a square. So this is where the difference is between modified Mohr and Coulomb Mohr. Okay, so no relief. Okay, and I think if you should have the points in there. No. Okay, so this is now showing all the theories on the same plot. Okay, so the modified Mohr theory is right here. This is the line we drew, and so you can see that this line now falls close towards those points, which were sort of between MNS or maximum normal stress and the Coulomb Mohr. Okay, so that's a better fit than the previous ones. Okay, so we did all three theories. Let's just see how we can apply them onto a problem. So this problem is taken from the question. Oh yeah, so there is a anomaly here. This is a point which does not fit on the line, and this is an experimentally observed part. And what we're trying to do is we try to fit a theory which will agree with the theories. Clearly, this point or this material does not fit, and so what you would do in this case is you will basically, when you're using this gray cast iron, you use a factor of safety such that you're never really coming anywhere close to it. So probably if you use SUC for gray cast iron, and if you design based on this, it's going to fail much before. So what you'll do is you'll have a factor of safety, and then you probably close it somewhere like this. So you will, this is where you will, this is how you will design something out of gray cast iron. Yeah, I kind of blanking on what these points are for which alloy, but they're not for gray cast iron. Okay, so here is the same problem as before, but now we've changed the material to brittle material. So the force F is applied at B as shown. Assuming that the material is brittle and the critical point of failure is A, like usual, compute the value of F, assuming Coulomb Mohr theory and modified Mohr theory. So the two brittle material theories. Assume that the tensile ultimate strength, which is SUT, is 31 kpsi, and then the compressive strength is 109 kpsi. So a big chunk of this problem we've already done. And so what I'm going to do is I'm going to find the stress. So let's get A.
So are all the other values basically the same in the problem?
Everything is same except with these. And then it is also a brittle material. It's not a ductile material. So A is going to be subject to stress sigma x. Sigma z is 0. And then there will be a shear stress another tau okay, and so we are also finding the stress on the smaller diameter and not the bigger one, which is 1.5, because the smaller diameter is the one which will break before the bigger one. And I think another assumption we'll make is there's no stress concentration at A. So I'm just pretty much going to go and copy paste the values I got earlier, because that part remains the same. That is the stresses at sigma x and tau zx. Okay, so we had computed the sigma x and tau zx previously. And when we did that computation, we put the right moment arm, right? This is the 14 and 15 of the moment arm for the bending moment and the torque. And then we computed these stresses in terms of force F, which is an unknown. We'll just take this. Okay, so before we apply Coulomb theory, let's just go to Coulomb theory for a second and see what Coulomb theory requires. It requires us to compute it here, yeah. So it requires us to compute sigma A and sigma B. What are sigma A and sigma B? They are principal stresses. If we go uh, to this theory, that is the modified Mohr theory, we also need sigma A and sigma B. So our first step is to find sigma A and sigma B, and then we can apply either of these theories. So let's just do that. So find the principal stresses. Okay, so sigma A B is equal to sigma x plus sigma z divided by 2 plus or minus sigma x minus sigma z divided by 2 square plus tau zx square. So I'm just going to plug in the values. Okay, so we end up getting, so if you use the plus sign, you get sigma A equals 175.8. Since you assume that sigma 1 is the bigger of the two values, in our theories, we should use the bigger value for sigma A, and sigma B is minus 33.2F. Okay, so what we can see is that if you plot sigma A, sigma B on that plot, since sigma A is positive, sigma B is negative, it's basically in this quadrant, the fourth quadrant. This is where the stresses live. Okay, so we need to use the theory, whatever the theory is for quadrant 4. So what I need to do is to use the first theory, which is the Coulomb-Mohr theory. In quadrant 4, the formula is sigma A divided by SUT minus sigma B divided by SUC equal to 1. And then that is 175.8 times F divided by 31 times 10 raised to 3. This is the tensile strength in tension. And then we have minus 33.2 F divided by 109 times 10 raised to 3 equals 1. And clearly that's one equation, one unknown. You can solve for F. Comes out to be 167 lbf. Okay, so the key is this, that in fourth quadrant, that's the equation. Okay, so I'm almost done. So now let's apply the modified Mohr theory. So in quadrant 4, so if you plug the equations, you'll see that they depend on the ratio of sigma B divided by sigma A. So it depends on so either you use this equation or you use this equation. They all depend on this ratio, right? Sigma B divided by sigma A. So let's just find that ratio. And I'm going to go 1 minute over time, but I'll be done with this. Let me try to finish this today. So let's find sigma B divided by sigma A. It comes out to be 175.8 F divided by minus 33.2 F. And I need to take the absolute value. And you can see that's greater than 1. My bad. sigma b is the smaller of the two, right? So it's minus 33.2 F divided by 175.8 F. So it is less than 1. Okay, so if it's less than 1, I just have to use this equation. S sigma A is equal to SUT. So I go back, I use the equation sigma A equals SUT, and sigma A is 175.8 F equals 31 times 10 raised to 3, and then solving for F, I get 176 lbf. Okay, so modified Mohr theory predicts the force can be slightly larger than the force due to Coulomb Mohr theory. Okay, so